The modern consumer is permanently tethered to a vulnerable, expensive utility grid, paying hundreds of dollars every month for basic survival. Meanwhile, traditional off-grid communities have quietly utilized localized aquatic physics for centuries to generate massive amounts of continuous mechanical and electrical power for free. No dams, no solar panels, no monthly bill. This practice is called aquatic harvesting, and the physics behind it are so simple, the real question becomes why almost nobody is doing it. Every month, the average American household faces a rising power bill, now averaging over $150, with some regions seeing annual increases that far outpace inflation. Over the last decade, residential electricity prices in the United States jumped from 13.4 cents to 15.3 cents per kilowatt hour, a 14% increase, while the cost of living crept up at less than half that rate. The numbers are blunt, utility rates climb, but reliability falls. In 2024, the average home endured 106 minutes without power, up from 92 minutes just 10 years before. Grid failures are no longer isolated to hurricanes or wildfires. Routine outages stretch across suburbs and small towns alike, driven by aging transmission lines, deferred maintenance, and overloaded transformers. Solar panels, once the favored escape from utility dependence, offer only a partial reprieve. Cloud cover, short winter days, and the ever-present risk of inverter or battery failure mean most solar homes remain tethered to the grid or invest thousands in lithium storage. A typical off-grid solar setup, sized to cover a family's nightly load, demands a battery bank costing $1,500 to $3,000 upfront plus replacement every 8 to 12 years. The promise of energy independence evaporates under the weight of replacement cycles, warranty claims, and the reality that even the best solar system sits idle half the day. Meanwhile, outage frequency and duration continue their upward climb, as documented by the IEEE reliability indices. The illusion of a dependable, affordable grid is unraveling. For those unwilling to accept rolling blackouts, ballooning bills, and the hidden costs of solar, the search for a continuous, self-sustaining power source is no longer theoretical. It is a matter of survival and economic sense. Hydroelectricity in the public imagination is synonymous with concrete walls, flooded valleys, and turbines the size of trucks. The reality is far simple and far smaller. For centuries, rural communities powered entire economies with nothing but a modest stream and a wooden wheel. 19th century grist mills scattered across North America and Europe ran day and night on vertical drops of just a few feet. No dam, no reservoir, no government contract, just moving water and gravity doing the work. These mills operated reliably through drought and storm, grinding grain, sawing timber, and pumping water with nothing more than a steady flow in a well-placed channel. The misconception that hydroelectricity demands a massive river or a dam. The size of a city block is a modern invention shaped by the marketing of industrial utilities. In practice, the physics of water power scale down without losing effectiveness. A net head of 2 to 5 meters, less than the height of a single-story house, can drive a small turbine or turn a belt with enough force to supply all the lighting, refrigeration, and basic appliances for a rural home. The millwrights of the past understood this intuitively. It is not the volume of water that matters most, but to the speed and vertical drop. Even a shallow creek, if channeled correctly, delivers continuous, predictable energy. Today's micro-hydro systems borrow directly from this legacy. Instead of wooden wheels, they use Pelton runners or turbo turbines built to spin at hundreds of revolutions per minute on modest flows. Permanent magnet alternators convert that rotational force into electricity with no need for batteries or fossil fuels. The entire system can be assembled for less than the cost of a single month of grid power in some regions. The myth of the mega dam is a barrier, and it collapses under the weight of historical precedent and the undeniable power of moving water. Water falling under gravity carries an enormous potential. The core equation, P equals rho g QH times efficiency, translates this raw physics into real-world power output. Here, P is power in watts, rho is the density of water, G is gravitational acceleration, Q is volumetric flow in cubic meters per second, H is net head in meters, and ETA is the total system efficiency, typically between 55 and 70% for modern microhydro. Net head is not just the vertical drop from intake to turbine, it is the gross elevation minus all friction and turbulence losses in the pipe and nozzle. Every meter of head counts. Consider a 100-foot vertical drop, 30.48 meters, delivering a modest flow of 1 liter per second. The theoretical output is 1,000 times 9.8, 1 times 0.00, 1 times 30.48, or roughly 299 watts. At 60% efficiency, and that is 180 watts of continuous real electricity, enough to run lighting, refrigeration, and basic electronics around the clock. Push the flow to 11.2 liters per second, and the same drop yields 3,350 theoretical watts. With typical losses, the net output lands near 2 kilowatts, rivaling the daytime surge of a full solar rooftop, but available 24 hours a day. The relationship is linear: double the head, double the power. Halve the flow, halve the output. This is why even a shallow creek, if it can be routed down a steep hillside, becomes a reliable source of energy. The design process begins and ends with these numbers: hardware sizing, pipe diameter, turbine selection, all follow from the available head and flow. A properly calculated net head is the master variable, dictating every downstream engineering choice. The theory is not abstract, it is the foundation for every successful microhydro system. From Amish workshops to modern off-grid homesteads, a 1 kilowatt microhydro system begins with the penstock, a length of pressure rated PVC pipe, typically 4 inches in diameter, running from the intake to the turbine. For a 30-meter run at 0.1 cubic meters per second, Schedule 40 PVC holds a pressure rating well above the 4-bar maximum, encountered even at 40 meters of head. Cost for this section, including solvent welded joints and intake screen, averages $120. PVC is preferred for its low friction coefficient and resistance to corrosion, and steel is reserved for high pressure or buried installations where pipe friction and UV degradation become secondary to mechanical strength. The intake must filter debris without choking flow. A fish, friendly mesh, 6 millimeters or finer, bolts across a concrete-filled intake box. Stainless steel nozzles with adjustable throats cost $80 each and focus the water jet, maximizing impulse on the turbine buckets. The nozzle diameter is calculated to match available flow and head, ensuring the jet velocity approaches 20 meters per second at 15 meters of drop. This kinetic energy is delivered directly to the Pelton runner. The Pelton wheel itself, a 400 millimeter cast aluminum or composite runner, $250 retail, part number PEL 401K, features precisely shaped buckets to split and reverse the water jet. Under a 15-meter head and 0.12 cubic meters per second, the runner spins at 550 revolution per minute, producing 260 Newton meters of torque. For lower head sites, a turbo runner offers higher revolution per minute at reduced torque with a modest efficiency penalty, but direct drive compatibility for smaller alternators. Mechanical power transfers from the runner via a keyed shaft to a permanent magnet alternator. The MGL 3500, a 3 kilowatt 48 volt direct current unit, is the workhorse of off-grid hydro. Retailing at $300, it operates at 92% efficiency at rated speed, dropping to 85% under partial load. Direct drive is possible for high-speed turbines, otherwise a single-stage helical gearbox. $150 steps up runner revolutions per minute to match the generator's optimal range with less than 3% loss. Power exits the alternator as three-phase alternating current or rectified direct current, depending on load requirements. For battery-based setups, an MPP charge controller, such as the TriStar TS45, $100, stabilizes voltage and maximizes output. Wiring, fuses, and mounting hardware add another $80 to $120, bringing the total bill of materials for a 1 kilowatt system to just under $1,000. Lower cost builds substitute a Turgo runner and smaller alternator, dropping the price to $620 at the expense of a 5% efficiency loss. On site, a homesteader stands beside the control panel, telemetry gear in hand. Digital watt meters and loggers track output, uptime, and system health. Real-world data confirm field reliability. Over 95% annual uptime, with downtime limited to filter cleaning and seasonal low flow. The system's mechanical simplicity, 2 bearings, 1 shaft, 1 alternator, translates into minimal maintenance and long service life. Every component, from PVC penstock to Pelton wheel, is off-the-shelf, open source, or easily fabricated by a local machinist. Receipts and parts lists from actual builds document the true cost, $500 to $1,000 for continuous 24-hour power and assembled in a weekend with basic tools and no specialized labor. This is not theoretical engineering, it is a blueprint for energy independence, grounded in physics and delivered by water moving under gravity. A lithium battery bank sized for true off-grid living is not a luxury, it is a necessity forced by the intermittent nature of solar. Industry-standard lithium iron phosphate modules, including the battery management system and enclosure, cost between $120 and $200 per kilowatt hour. For a typical 10 kilowatt hour battery pack, the upfront price lands between $1,200 and $2,000. Stretch that to 20 kilowatt hours, and the outlay doubles. This is before the cost of the solar array, the inverter, the charge controller, or the wiring hardware that pushes a fully independent solar setup well past $5,000, even with careful sourcing and do-it-yourself installation. The true cost is not just in the purchase. The median warranty is 8 to 12 years, and field data from homesteader forums confirm that most banks are swapped by year 10. Over a 20-year window, the battery line item alone can reach $3,000 to $6,000, not counting disposal fees or the environmental cost of spent cells. Microhydro upends this math. A properly built system drawing from a modest stream with a vertical drop of 3 to 5 meters delivers power every minute of every day. No battery bank, no charge controller, no inverter cycling, and no depth of discharge worries. The alternator spins, the lights stay on, and the refrigerator hums through the night. For $500 to $1,000 in materials, including a PVC penstock, a Pelton runner, a permanent magnet alternator, and basic mounting hardware, an entire household can be powered with no storage at all. The continuous output is the difference. When water flows, watts flow. There is no need to overbuild for cloudy days or undersize for winter. The system's output is as steady at 2 a.m. as it is at noon. Levelized cost calculations drive the point home. The U.S. Department of Energy's own figures put the lifetime delivered cost of lithium storage at 12 cents to 20 cents per kilowatt hour. Microhydro, once installed, delivers at zero marginal cost. Over a decade, a $1,000 microhydro turbine running at 500 watts produces more than 43,000 kilowatt hours, enough to power a home for years, at a hardware cost of less than 2 cents per kilowatt hour. The only recurring expense is routine maintenance, a tube of grease for the bearings, a replacement nozzle or two, and the occasional flush of the intake screen. Real-world field logs from off-grid sites in Oregon and British Columbia show annual uptime exceeding 95%, with outages measured in hours per year, not days. The economics are not theoretical. One homesteader in the Cascades running a 1.2 kilowatt Turgo turbine on a 12-meter head reports continuous output every day but the driest weeks of late summer, and his total build cost was $950, assembled with off-the-shelf parts and no specialized labor. The system has run for 5 years with only a single alternator bearing replacement. By contrast, his neighbor's solar array required a $2,400 battery swap after 9 years, plus a $600 inverter replacement after a lightning strike. The micro hydro system never missed a night, never needed a generator, and never left its owner in the dark. This is the quiet revolution. A modest stream, a calculated drop, and a handful of mechanical components yield uninterrupted, decentralized power. The battery bank becomes obsolete, the grid's rolling blackouts, and the solar system's 2 a.m. silence are replaced by the constant presence of moving water and spinning metal. The numbers are blunt, the physics unyielding, and the outcome is clear. In the economics of independence, continuous power wins. A hydraulic ram pump operates without fuel, wiring, or external power, and its only inputs are a modest vertical drop, typically 6 to 8 feet of head, and a steady flow of water. In Amish communities across Lancaster County and Holmes County, these pumps are buried assets, delivering water uphill for livestock, dairy barns, and household cisterns. The design is brutally simple: 2 moving parts, a waste valve and a delivery valve, hammer open and shut using the inertia of falling water to generate a pressure spike. This impulse drives a fraction of the incoming flow up the delivery pipe, often lifting water 20 to 30 feet above the creek bed. Field measurements confirm the numbers. A standard 1-inch ram with a drive head of 7 feet and a flow of 8 gallons per minute routinely delivers between 3.5 and 4.5 gallons per minute at the outlet. That is over 2,000 gallons per day, enough to fill a cistern or supply a dairy operation, all without touching the grid. Efficiency hovers between 25 and 35%, but the trade-off is relentless reliability. Amish operators resurface valve seats with brass or steel, keep drive pipes at optimal length, and rely on communal maintenance. Ram pumps are often installed and serviced by family-run metal shops or local technicians listed in county extension bulletins. A historian specializing in rural technology notes that the hydraulic ram is not just a tool, but a cultural anchor. It embodies the Amish ethic of self-sufficiency, robust, repairable, and utterly indifferent to blackouts or fuel shortages. Unlike solar panels or battery banks, the ram pump's only maintenance is the occasional valve replacement or pipe flush. Its continuous operation is enforced not by software, but by physics and gravity, a mechanical promise kept for generations. Permit applications for micro-hydro installations routinely trigger a gauntlet of regulatory scrutiny, regardless of scale. In county planning departments from Oregon to Pennsylvania, even a 2-inch PVC penstock designed to divert less than 0.2 cubic feet per second can be flagged as a potential threat to watershed integrity. Official denial letters cite cumulative impact as the operative phrase, invoking the risk that many minor diversions might, in aggregate, alter stream flow or degrade aquatic habitat. In March 2023, Douglas County, Oregon, rejected a 4-inch penstock for a 300-watt Pelton turbine, stating the project would exceed the cumulative impact threshold for the lower river watershed and could impair fish passage. A similar refusal in Greene County, Pennsylvania, referenced a 2-inch PVC pipe and concluded the alteration constitutes a material change in flow regime. The cumulative impact on the watershed's hydrology cannot be determined at this time. Environmental regulators defend these decisions by pointing to state water rights statutes and the National Environmental Policy Act, which mandate that any stream alteration, even one supplying a single off-grid home, undergo environmental review. The language is deliberately broad, granting planning commissions wide latitude to block projects that fall outside established utility channels. One county planner, interviewed on record, explained, "We are not just evaluating a single pipe. We are projecting the effect if every property owner on the creek did the same. The law requires us to consider the watershed as a whole." For homesteaders and underground organizers, these denials are more than bureaucratic hurdles. They are existential threats to decentralized power. The technical reality is stark. A 2-inch penstock costing less than $80 in materials can deliver enough head pressure and flow to generate continuous wattage for an entire household. Yet the regulatory apparatus treats it as a potential hazard, not an engineering solution. The result is a standoff, private innovation forced to operate in the shadows, while official policy clings to the logic of centralized control. Every off-grid organizer knows the checklist by heart. Divert a fraction of a stream, never enough to dry a creek bed, always less than 10% of low season flow. Use a fish-friendly intake screen, 6 millimeters or finer, to let fry and debris pass. Route water through pressure rated PVC no wider than 4 inches, and return it downstream within 100 yards. The impact is surgical. The stream's chemistry and temperature remain unchanged. The aquatic habitat undisturbed. A single 2-inch penstock delivers enough head and flow to power a household, yet vanishes in the grass when the job is done. No concrete, no reservoir, no scars on the land. The entire system is assembled with hand tools, often by a family or a small crew. Maintenance is a quarterly filter cleaning and a shot of grease for the alternator bearings. If the system needs to be removed, it leaves behind only the original stones and soil. This is the low-impact ethic, mechanical self-sufficiency without ecological footprint. For those ready to act, the tactical steps are clear. Survey for vertical drop, measure minimum flow at the driest season, source off-the-shelf Pelton or Turgo hardware, and keep every diversion temporary and reversible. The blueprint is open source, the math is public, and the path to independence starts with a tape measure and a willingness to ignore the myth that power must come from above. The grid's fragility is not your burden. The creek is waiting. Grid fragility is not a theory, it is a fact. Right now, a $1,500 micro hydro build using 2-inch PVC and a Pelton wheel can deliver power 24/7, while most solar rigs stall at dusk. The only real barrier is regulatory interference, not physics. In a world addicted to intermittent, overpriced power, continuous flow remains the ultimate act of engineering defiance. What system would you trust when the lights go out?